All right. Well, good evening and welcome to Lecture 5 for MT225. This one's a pretty important lecture. Lots of important stuff here. Probably one of the most important, if not the most important, basic skill that we need to have available to us to solve practical problems. That's what we'll be covering tonight. So let's proceed. Um, got all the regular content there, or the course information, so everyone should be able to access that. I haven't heard any problems so far on this, so it seems like everyone's getting access. I'm seeing views on the videos I'm posting on the YouTube channel, so people are evidently finding those, so that's fine. Homework 1 is due tonight, so by 11:59 p.m. tonight, make sure I've got a copy of it, either by email or by text, as long as I'm going to be able to see it and in some sense grade it. It's not like I'll be able to actually hand back copies to you, but what I usually do is write up a little grading summary that I'll email to you when I'm done with the grading, and should have that to you before we get to class on Monday night. Make sure it's something I'm going to be able to read. If you send, I've already had, I think, 3 people so far already turned in their assignments. So if you haven't done so already, you still have some hours left on that. And I'll open up the floor for questions on that homework assignment here momentarily. Homework 2 has been posted. That's due same time next week. So 224, that would be next Wednesday evening, and that covers the content that we've gone over this week. So vectors, vector operations, and what we'll be doing tonight. We will also be doing quiz 1 on Monday night. Now, unless something extraordinary happens and we have access to a room, by Monday night, we'll be doing the quiz a little bit differently. I'll post the quiz on the class website on Monday, and we'll treat it just kind of like a homework assignment. Just have it set up and email your answers or text your answers in on it for submission. We'll figure out what the parameters will look like, what the timing will look like that on Monday. But we'll be issuing some sort of quiz relevant to homework 1. So the only thing it'd be testing would be content from homework 1. You'll also be getting your grades on homework 1 on Monday, so you'll have a chance to see where you might have needed to do a little bit of improvement. So far, the results coming in look pretty good. Any questions on the homework? All right. Well, I'll assume the silence means that for the most part, everything was fine. It should have mostly been review. Maybe the simultaneous equation stuff was a little bit different, but for the most part, it should be skills pretty much everyone has. So if you just make sure if you haven't turned that in yet, you get that in before midnight, or it won't be counted. So let's proceed. Let's take a look at our content for tonight. So we're going to start off with a little bit of review of coordinate systems. I know most of you have seen the first coordinate system we're going to look at before, but may not be as familiar with the second one. Both are just different ways of describing mathematically and numerically locations or positions that we're going to also use with respect to vectors. So we'll review coordinate systems and the ideas behind those. We'll look at the tools we're going to need for doing vector math analytically. So last time we learned how to do vector math graphically by drawing arrows and connecting tails and heads. That's good for pictures, good for rough visualization, but it's not precise enough for real work. So we're going to learn the precision tool tonight, and we'll do some examples of the fundamentals on that, and then we'll do some calculation practice. So the fundamentals, we have to learn about what components are, how we can break a vector up into its components or its pieces, and how we can put together the pieces back into a whole quantity that we call the resultant. And those two ideas form the basis of vector addition, which is what we'll be doing hundreds and hundreds of times for the remainder of the semester. And so we'll spend the rest of the evening doing some vector addition practice. I'll do some examples, and during our practicum session, I'll post some sample problems, and you can work on those live. I'll usually give you 10 minutes or so to work on one, then I'll give you an opportunity to ask questions about it, then I'll work it out. And the practicum session problems will also be posted in a separate video. I usually stop the video at break, and then we start another video for the practicum session after our break is over. So a little bit different setup. So let's take a look at coordinate systems. Now, we've worked with in the A&P program what we call the Cartesian coordinate system, and that's the first one we'll take a look at here. Any coordinate system, and there are lots and lots of them out there, provide references for measurement. Essentially, it's used to represent pieces of information in different ways. We learned last time that a vector has more than one piece of information to it. It has a magnitude and a direction. It has a size and a direction to it. A coordinate system can be used to represent that because coordinate systems represent multi-dimensional quantities, quantities that require more than one piece of information to represent. We use reference axes to represent those quantities, essentially number lines. And there are two coordinate systems that are most common out there, and we call them the Cartesian coordinate system and the polar coordinate system. Cartesian is most likely what you've used before. I know it's what you've used in the A&P program. Anytime you look at a graph or a chart or a plot of something, you're typically using the Cartesian coordinate system. If you've plotted data on a set of axes, you've used the Cartesian coordinate system. Polar might be a little bit different to you, might be something you haven't seen before, but we'll take a look at it. And we'll see that both of these lend themselves very well to representation of vectors. So let's look at Cartesian first. This dates back to 1637, René Descartes. Such an important innovation that the whole science of map making is named after him. The cartography comes from Descartes, from his name. His idea, which was pretty revolutionary at the time, was to use two perpendicular number lines to measure the locations to a point in a plane. In a plane, in a flat surface, if you're trying to get from some starting point to that location, you generally need two pieces of information to do that. If you think about navigating on the surface of the Earth, you've got latitude and longitude. Those are two pieces of information. If you know the latitude and you know the longitude, you know where you need to go. You know what point in that surface you're supposed to be at. Well, that's basically what the Cartesian coordinates do. They give you two numbers, and those two numbers are uniquely identifying a single point. So the Cartesian coordinate system, that's what you've used as the XY coordinate system that you've probably seen come up in math courses. And it allows us to identify a point in a plane, a flat surface, by two numbers. Now, those two numbers tell us distance along a reference. So one tells us how far we go along the horizontal axis, and one tells us how far we go on the vertical axis. You could think of that like how many miles east or west versus how many miles north or south if you're navigating by coordinates. So we have two numbers, an X and a Y coordinate, that give us the location of a single point. And there's the plane divided up by the axes. We have our horizontal axis, what we usually call the x-axis for short, and we have our vertical axis, the y-axis for short. Those two cross at one point, what we call the origin, And the origin is essentially arbitrary. One big difference between, I suppose, math classes and engineering classes is in math classes, they seem to really focus on the origin and really measuring everything carefully from the origin and all of that. In science and engineering courses, we tend to have a lot more freedom with what we do with the origin, and in fact, what we do with the coordinate system. Coordinate systems can be relatively flexible, and it's in many problems we'll have to choose the best coordinate system to make the problem, to solve the problem. The a good choice of a coordinate system can turn a difficult problem into a fairly easy problem, and we'll see several examples of that here coming up in the next few weeks. Now, the other thing they kind of focus on a lot in math classes are what we call the quadrants, the first, second, third, and fourth quadrant. We don't really worry too much about quadrants specifically in this class. What we do worry about is sign, sign as in positive or negative. When we deal with horizontal values, x values, positive generally means to the right, while negative means to the left. Similarly, for the vertical axis, for the y-axis, positive generally means up, and negative generally means down. The signs are going to be important. We're not going to really worry too much about saying, well, we're over here in quadrant 3 or we're over here in quadrant 4 or 1. We're more interested in knowing, well, is x positive or negative? Is y positive or negative? And if to the right is positive and to the left is negative, up is positive, down is negative, that'll generally keep things straight with respect to signs. So that's the Cartesian coordinate system. So any point in the Cartesian coordinate system we can assign two numbers to, and or vice versa. With two numbers we can locate a single point. So let's go over to the paper here. If I draw a set of coordinates on here, set of axes, we usually label those x and y. So any particular point, say for example, that point right there, I can assign coordinates to by measuring how far I'd have to walk along the x-axis to line up with that point, and how far I'd have to walk along the y-axis. So maybe I have to go 2 units to the right, and then maybe 4 units up. 1, 2, 3, 4. Something like that. So we've got 2 units to the right and 4 units up. That gets me to the point. Now we could identify that point with an ordered pair of numbers. We could say 2 and 4. That would mean 2 units to the right and 4 units up, whatever the measurement is here, whether it's feet or miles or any other unit. But what will work best for us in this class is to think about it just like I've drawn it out here, using arrows. I'd go to the right 2 and then up 4. So the 2 is really this part down here. It's that horizontal arrow, and the 4 is really the vertical arrow. We could label the sides on that, how far we are in each direction. And we'll come back to that here in a little bit. Let's put another one on here. Let's say we've got something like 4 to the left and 3 up. So 4 to the left, could draw an arrow with length 4 to the left, and then an arrow with length 3 up. That would get me to that point right there. So the idea is that we need 2 pieces of information to get to those points: how far to the right or left, and how far up or down. And I drew these very specifically with arrows for an important reason that we'll come back to here in just a moment. So let's go back to the notes and look at polar coordinates. Now, polar coordinates you may not be as familiar with, but polar coordinates do the same job as Cartesian coordinates. They let us identify a point with two numbers, with two pieces of information. In polar, we use instead of length along one axis and then length along another, we use one length. How far away is the point from the origin? That is the length. And then we put that together with an angle, with a direction. A little bit different than Cartesian. In Cartesian, we had two numbers and both of them were lengths, both of them were distances. How far to the right or left, how far up or down. In polar, the two numbers are a length and an angle. The length is the distance from the origin to the point, and the angle is what direction we're going in. That distance from the origin to the point, we call the magnitude. Magnitude is the value of the distance between those 2 points. So it's how big the distance is between the origin and whatever point we happen to be interested in. Direction is given by an angle. If you've dealt with angles in math classes before, maybe you've even had a physics class where you've dealt with vectors, you may have always referenced your angle to the same point or to the same line, usually the positive horizontal axis, the positive x-axis, and you measure your angle counterclockwise. We have a good deal more flexibility here in this class, so we're going to pick whatever angle happens to be convenient. And that means it has to have a specified reference. You can't just say, well, 30 degrees. 30 degrees measured from where? You have to have some sort of reference as to where that angle is measured from. And we'll see that here in some examples. So you can think of polar coordinates kind of like navigating by compass. If you have a compass, or you're even say flying a plane using a magnetic compass, you might turn to a heading of 030, 30 degrees, and fly for 10 miles. That'll get you to a point. Those are the polar coordinates of that point. You could also look at it as north, south, east, and west. How far to the north or south, how far to the east or west? That would be the Cartesian view of that same point. Both Cartesian and polar give us the same information. They just give us that same information in a different format. In Cartesian, we get it in two distances. In polar, we get it in a distance and an angle. So there's the picture of a point being located by a magnitude and a direction. Capital M there representing the distance between the point and the origin, and the angle, that being represented by the Greek letter theta, is drawn there. This brings up a pretty good point that a picture can often be very helpful. When you're trying to draw things out or trying to describe a vector or a point in space that you're locating by polar coordinates, just reading off angles may not be enough. You have to have some sort of reference. A picture usually locks everything down. If you draw a picture out, then it's pretty clear where your angle is referenced to. In this case, my angle theta is measured counterclockwise from the positive x-axis. Without the picture, I'd have a question as to where that angle is measured from. Is it clockwise or counterclockwise? Is it from the y-axis or from the x-axis? You don't necessarily know without having that picture. So when in doubt, draw a picture. If you draw a picture out, it will most often explain everything. So let's go back to the page here and see how this relates. So let me draw a much bigger version here. I'm going to zoom in kind of on the first quadrant. So we have our x and our y, and I've got this point over here. And let's say that point in Cartesian is, let's say, 5 units to the right. Change that actually. We'll make that 4 units to the right. And we'll make that point right there 3 units up. That's the Cartesian description of that point. 2 numbers, 4 to the right and 3 up. And we saw last time that these arrows represent vectors. And that when I've got a pair of vectors arranged like this, head to tail, we're kind of setting up for addition. And physically, what we're doing here is we're combining the results of 4 to the right and 3 up. If these were a pair of forces, we could have 4 pounds pulling to the right while 3 pounds pull up. Well, we can add those two together. And we learned last time adding graphically just involves arranging the vectors head to tail and then drawing an arrow starting from the tail of the first vector and going to the head of the last one. So this vector that I've drawn off at some angle is going to have some magnitude. And now if you're thinking here, you can see the connection between polar and Cartesian. These get us both of these descriptions get us to the same point. The Cartesian description is looking at describing that point by 2 vectors, essentially, a horizontal plus a vertical. A horizontal vector 4 units long and a vertical 3 units long. The polar description is giving us that point in terms of 1 vector, some distance at some angle. Now, knowing what we know about triangles, we can figure out what the magnitude and the direction are here. And we'll be doing that as an example here in a little bit, but we could use the Pythagorean theorem, for example, to figure out that the magnitude here would have to be 5. The angle, what we'd do with that is use an inverse function. We'd use one of the inverse trig functions. And I would encourage you here, in fact, I'm going to tell you about the only way that we do this is by using inverse tangent. Inverse tangent is going to be the safest way to figure out that angle because we know these 2 numbers. If we screwed up and calculated a bad value here and then tried to figure out the angle based on that value, we're going to get a bad angle too. But tangent involves the opposite over the adjacent. So inverse tangent of opposite over adjacent will give us the angle. So our angle here, in fact, I can write down a couple of equations here that'll be pretty important to us. The magnitude, that's the Pythagorean theorem. It's the square root of the whatever the opposite side is squared plus whatever the adjacent side is squared. In this case, 4 squared and 3 squared. And then we took the square root of it. That's how we always get the magnitude. Square the 2 legs, add them together and take the square root. The angle is going to be the inverse tangent of the opposite over the adjacent. And if we run over to our calculators here, the opposite side is 3, the adjacent side is 4. So I have the inverse tangent of 3 over 4, and that gives me 36.870 degrees. So for this point, whatever this point is, in Cartesian, the point is 4 to the right plus 4 and 3 up plus 3. In polar, it's a magnitude of 5 and a direction of 36.870 degrees. Two pairs of numbers in both cases, because vectors are two-dimensional quantities. We have to have two values, two pieces of information to describe them. And Cartesian gives us those two pieces of information in terms of distance along the x-axis and distance along the y-axis. Polar gives us those two pieces of information in terms of a distance and an angle. Drawing both together on one set of axes shows us the connection between the two. The polar description and the Cartesian description are really just looking at the angles and sides of a right triangle. When we look at the legs of the triangle, we're dealing with the Cartesian description. When we look at the hypotenuse and an angle, we're looking at the polar description. And that gives us our major tools for converting from a polar description to a Cartesian or vice versa. So, for example, and I don't think this is written explicitly in the notes, so I'll write it out here. If you're going from Cartesian to polar, so you're going from your x's and y's, your horizontal and vertical, those are the two equations up there to use. If you know your opposite and adjacent sides, you can use the opposite and the adjacent side in the Pythagorean theorem to get your magnitude, and you can use the inverse tangent to get your angle. If you're going the other way, if you're going from polar to Cartesian, there you'd have a magnitude and a direction, and you want the legs. Well, that's about our most common trig problem out there. When we know the hypotenuse and we know the acute angle and we want the legs. The opposite side comes from sine. The adjacent side comes from cosine. And we have written it out in the past. When we looked at trig last week, we said that sine of an angle was the opposite over the hypotenuse. Hypotenuse here is the magnitude, so we'll call that m. And the cosine is the adjacent over the magnitude. And that's how you've used trig before. We're going to change that now. We're going to write it a little bit differently. We're going to cross multiply this out because that's going to be the way we're always going to use it. So we want the opposite directly. So when we cross multiply this out, and this will give us our two equations to convert from polar to Cartesian, when we want the opposite side, it's going to be the magnitude times the sine of the angle. And when we want the adjacent side, it's going to be the magnitude times the cosine of the angle. So no more just going to the ratios. We can write it all out directly. Opposite is sine times the magnitude, adjacent's cosine times the magnitude. So to go from Cartesian, when we have the x and the y, the legs of the right triangle, we use magnitude and direction. Magnitude from the Pythagorean theorem, direction from inverse tangent. When we've got the magnitude and direction, we know we're dealing with a magnitude of 10 and an angle of 30. We can use that magnitude of 10 and an angle of 30 to figure out the opposite and the adjacent sides. So these two pairs of equations give us the tools we need to convert from a polar description to Cartesian or to convert from Cartesian to polar. And in practically every problem, we end up doing both. Because when we combine vectors together, it's easiest to combine them using the Cartesian descriptions. But it's easier usually to describe a vector in polar. It's magnitude 10 at angle of 30. That's typically how we describe the vector. To do calculations with it, what we do is break it up into Cartesian by using our definitions of sine and cosine. We do the math there, and then in the end, we convert back from Cartesian to polar using our magnitude and direction. So let's see how that works with some actual numbers. The first skill we have to develop, knowing now how these coordinate systems work, is to break a vector up into components. When we break a vector up into components, we are essentially trying to find the legs when we know the hypotenuse and an angle. So this is the key step in order to do vector addition with math rather than with graphics. While a graphical method does work, it isn't very precise. And for practical applications, we have to use some sort of analytic method, something we could use our calculators for, rather than using rulers and protractors to figure things out. Vector calculations are the main application of trig. And that's the main application of trig in this class, and it's the main application of trig in pretty much everything. Almost every time you're using a sine or a cosine, it's about figuring out the legs of a right triangle from the hypotenuse. And that's basically what we're doing in working with vectors. So some terminology to be familiar with here. Component. We talk about components all the time. Everyone in maintenance should know what a component is. A component is a piece or a part of something. With respect to a vector, a component is how much of that vector is along a particular direction. So usually those particular directions are the x or the y axes. So for example, here on the sheet, we've got this vector magnitude 5 at an angle of 36.870. Its horizontal component has a length of 4. Its vertical component has a length of 3. It's how much of that vector lies along one direction or another. Those are the components, the pieces of that vector. When we break a vector up into its components, we're doing what's called resolution. We're resolving a vector. Resolving or resolution is about being able to separate things. We talk about resolution on things like TV displays and so on, or optical resolution. It all dates back to being able to tell the difference between a point light source or two light sources that were really close to each other. Resolution's about being able to see things in detail and break things apart into their individual pieces. And that's exactly what we're doing with a vector. When we resolve a vector, we're breaking it up into its components along directions that we get to pick by defining our coordinate system. Usually, in almost every practical problem, that's going to be horizontal and vertical. Horizontal and vertical are the most natural choices for directions to have our components lie along. Not always the best choice, but it is the most common choice. So that's what a component is. And to get the components, we use the sine and cosine functions. The opposite side is the magnitude times the sine of whatever angle we're dealing with. The adjacent side goes with cosine. So the advice I gave you a week or so ago about trig and remembering the equations was to burn into your brain, sine goes with opposite, cosine goes with adjacent. If you're used to thinking about x and y, and you like to think, well, y goes with sine and x goes with cosine, be very careful. That isn't always true. It's true in a math class, because in math classes, we make very restrictive choices about how we're going to lay out the angles. But here in engineering, we have to be much more flexible, and we're going to use whatever convenient angle, whatever angle is most convenient to us. So opposite will sometimes be vertical, but other times opposite's going to be horizontal. It depends on how the angle is drawn, whether the angle is referenced to vertical or to horizontal. So don't get too tied up in X going with cosine and Y going with sine. Think instead opposite goes with sine, adjacent goes with cosine. On the other side of that operation, going the other way, we have what we call the resultant. The resultant is building up a vector from multiple vectors acting together, essentially the result of vector addition. And when we do vector addition, we always work on the components. While it's possible to do vector addition without working with components, if you're familiar with the law of cosines, for example, you're basically doing vector addition without dealing with components, but that's not a requirement for this class. In our class, we're going to always do vector addition by working with the components. In the end, we have to bring the components back to a magnitude and direction form in building the resultant. So the resultant vector is almost always going to be given as magnitude and direction. And that magnitude and direction are in polar coordinates. So we have to go and use the Pythagorean theorem to get from the opposite and the adjacent side to a magnitude, and use the inverse tangent to get the angle. So let's see how this works. Let's first practice on forming components. So let's take a vector. Let's say it's got a magnitude of 10. And since almost all of our vectors are going to represent forces, it would be natural to call this 10 pounds. But right now we're still kind of more in a mathematical kind of phase of things. So I'm going to eliminate the units for now. But next time when we get into working with force systems, we'll be dealing with vectors that are forces, and we'll have to have units in the calculation. Now I'm going to define a coordinate system here with my origin right there at the beginning of that 10 unit vector. Horizontal, that'll be my x direction, and vertical, my y direction. Then I've got this vector, magnitude 10. Now that's not enough information. Remember, vectors need two pieces of information. 10 isn't enough. I need to have an angle here too. And that angle, I'm not going to just call it theta, we'll make that 30 degrees. Now what we want to do is break this vector up into its components. Effectively, we're going from polar to Cartesian. And to go from polar to Cartesian, we're finding the legs. We're using sine and cosine to find the legs. So let's take a little bit of a different color here. There's our horizontal component. We'll call that x. Pull up a red pen that works. So our x component, or our horizontal component, be right there. And then our y component, or our vertical component, be right there. So we could call this y and x. We could also label them as we would a right triangle's legs. If we're going to work with the angle 30, this would be the opposite side, and that would be the adjacent side. So let's see how it works. Let's get the focus a little better. There we go. So let's see how this works. Let's find the adjacent side first. Doesn't really make any difference which side you find first. The operations are independent of each other. Adjacent goes with cosine. So the adjacent side is the magnitude times the cosine of whatever angle I'm dealing with. And My magnitude here is 10. My angle is 30 degrees. If I go to my calculator and key that in, cosine of 30 is 0.86603. So this is 10 times 0.86603, which would be 8.6603. So that's how much of that 10 unit vector lies along the x direction. If this was wind speed, we have a 10 knot wind at 30 degrees, we'd have 8.6603 knots blowing right down the x-axis. That'd be how much of that wind speed lies along one direction. So we get the adjacent side from cosine. The opposite side we'll get from sine. It's the magnitude times the sine of our angle. So our magnitude is 10. And if we go over to the calculator, we can figure out sine of 30. Sine of 30 is 0.5. So we have 10 times 0.5, which gives us 5. So the opposite side is 5. That means that if this was a 10 knot wind, we have 5 knots blowing across our x-axis or in the direction of the y-axis. If this is a 10-pound force, then that 10-pound force pulling at 30 is the same as 8.6603 pounds pulling horizontally and 5 pounds pulling vertically, since those two added up in a vector sense, x plus y, gives us 10. So we have 8.6603 there and 5 there. So those are the components of that vector. We found the components by using the magnitude and the direction. By using magnitude and direction and sine and cosine, we can find out what the components are. So that is the process of resolution. And you'll get to a point, we'll do enough of these problems where you won't have to do the whole formal write-up of saying magnitude, cosine, angle, and then filling it in. I would encourage you to do that until you feel comfortable enough with it to just jump right to your calculator. If you're already there, by all means, go with it. But most of the time, all we really need is this number here at the end. So if you can jump right to your calculator and say, okay, my adjacent side goes with cosine, so 10 cosine 30, plug that in, get a number, you've got what you need. So that is the resolution of a vector into components. Let's try another one here. Let's take a we'll take this one here, and I'll put an angle in there of, let's say, 40 degrees. And we'll make that 8. So that is our second vector. We've got a magnitude of 8, 40 degrees counterclockwise of the positive y-axis, off the positive y-axis. We want to break this up into horizontal and vertical as well, into an x and a y component. The practice I would encourage you to get into here is drawing up the components first and then figuring out the values. And you'll always want to draw them so they enclose the angle that you've been given. Certainly we could go x and y here, just like I did in the other problem, but then I'm going to have to figure out what's this angle. Now, you might know those two have to add up to 90 degrees, so that's got to be a 50-degree angle, but I guarantee I've given enough exams and problems and seen enough issues with errors in calculation to know that there's a non-trivial percentage of people out there that are going to write 60 there instead of 50, because people have this tendency to want to add to 100 instead of 90. Why take the risk? Use the angle that you're given. Don't try to translate it and then run the risk of screwing up something simple and causing the problem to be completely off. So what I would do, and I'm going to use a different color for this one, hopefully it shows up pretty well on the display. I'm going to go Y first, and then X. That way, my two component vectors enclose the angle I'm given, and I don't have to go figure out a different angle to work with. So this one would be my Y component, and that would be my X component. Remember, when dealing with vectors, the origin really doesn't make much of a difference. And so it doesn't really matter if we go vertical then horizontal or horizontal then vertical. So we may as well pick what's most convenient for us and what's going to be easiest to work with. It's one of those things that I've had some difficulty with people in the past on, because people tend to come from math classes, and math classes are generally very rigid about how you proceed and what order you do things in and all of that. Here it's much more flexible, so we can pick what's most convenient rather than what would be strictly done the same way in each problem. We can mix it up a little bit and use the problem to our advantage, set things up as efficiently as possible. So let's figure out this one here. Here's our 40-degree angle. So first thing we got to be careful of is what's opposite and what's adjacent. This is my opposite side, and that's my adjacent side. Here, X is opposite and Y is adjacent. That's okay. There's nothing wrong with that. So you just have to be aware of what's adjacent and what's opposite, so you pick the right trig function. If I go with opposite here, opposite goes with sine. So opposite is magnitude times the sine of my angle. My magnitude is 8. My angle is 40. And if we go over to the calculator and key in 8 sine 40, I get 5.1423. So that's the length of my opposite side, 5.1423. Then I've got my adjacent side. Adjacent goes with cosine. So that's magnitude times the cosine of an angle. So we've got 8 cosine 40 degrees. And according to the calculator, that's 6.1284. So those are my components of my of this vector with magnitude 8 and angle 40 degrees counterclockwise from the positive y-axis. If this was a force, then that 8 pounds pulling to the upper left at 40 degrees is the same as 6.1284 pounds pulling up and 5.1423 pounds pulling to the left. So we've broken up the vector into its components. Any questions so far? Anything not quite making sense? All right, so let's take it a step further. Let's look at vector addition. So we'll get to the main meat of the presentation here, vector addition. So I've put a procedure together here in the notes about how we can do this step by step. The procedure for adding 2 vectors, or really any number of vectors, and in fact, we'll be dealing with problems where we have more than 2 vectors that we have to add together. Sometimes we'll have 3, 4, 5 vectors we have to add together. That's okay. We can use the same procedure for it. First thing you have to do is pick a coordinate system. You have to decide what's X and what's Y. You can't build the legs of a right triangle unless you know what the angle is to that hypotenuse, and you don't know what that angle is until you decide what's horizontal and what's vertical. So you have to define a coordinate system. We can sketch the vectors out with their tails at the origin, just so that we can see them a little more clearly and put them on the same set of axes. We break each vector up into its components. So we resolve each vector down into its individual components in the X and the Y direction. Then we combine them by adding all the X components together. Though we have to take into account signs. We have to take into account direction. When we're dealing with number lines, which is essentially what these axes are, we have two possible directions. We either have left or right. We have up or down. If two components are in the same direction, then they add up. But if two components are in opposite directions, then they subtract. So part of the combination procedure here is to add all of the X components together. But when we do that sum, we write in the correct signs. If a component is to the right, it'll go into the sum as positive. If it's to the left, it'll go into the sum negative. That'll get us the right signs for our resultant components. So step 4 and step 5 here both involve doing what we call mathematically a summation. We're going to sum up the X components and sum up the Y components. But those X and Y components, those are vectors too. They have a direction to them. It's just a simple direction, left or right, or up or down. And it's simple enough that that direction can be represented with a sign. Positive for the right, negative for the left. Positive up, negative down. Then we have to finish up by constructing our resultant vector. And that's where we use the new components that we've calculated. When we sum up the X components, we get a new X component. When we sum up the Y components, we get a new Y component. It's the Y component and the X component of our new total vector, our resultant vector. Almost always we want that in terms of magnitude and direction. So we use the Pythagorean theorem to get the magnitude, and we use the inverse tangent to get the direction. So let's see how that works. So let's go back to the page here, and we'll see how that can work. So we've got two vectors laid out on the page already. I've got my red vectors and blue vectors, the magnitude 10 at 30 degrees and the magnitude 8 at 40 degrees. Now, before we go any further with this, let's use our skills from last time and draw out what the sum is going to look like. So if I sketch roughly, and this is a nice trick that can help you on homework number 2. If I want to add two vectors together, one way to do it is graphically. If I want to get the scale right, and it's going to be hard to see on the camera, but you'll be able to see it. If you put a blank sheet of paper over your original vector, you can trace it out fairly easily, rather than having to break out a ruler and try to line everything up and measure it all. So that's our magnitude 10 vector at 30 degrees. If I want to now add that 8 vector, that 8 magnitude vector, all I have to do is place the tail of that magnitude 8 vector at the head of the magnitude 10 vector, and I can sketch it out. You have to get the angle right, so it helps if you can see through the page and translate it around so you don't change your directions too much. Now I can sketch out that magnitude 8 vector. So that's our 8 at 40 degrees. My sum is going to be the vector from the beginning of the 10 to the end of the 8. So it's going to look something like that. So that's what my resultant vector is going to look like. 10 plus 8 is going to give me whatever this is. Now, just doing this graphically, I'd have to break out a protractor and figure out what this angle is, or I'd have to break out a ruler and measure to scale what this length is to try to get the right values. We're going to get the numbers for this vector mathematically, but it can help us visualize what to expect. So here I'm going to expect an answer that's kind of up like that, up and to the right. It's going to have a bigger y component than it has x component. And it's going to be at a fairly small angle to y or a fairly big angle to x. This is where the benefit is of doing graphical vector addition. You can get some preview of what your answer is going to look like. And that helps to check whether you've done your calculations correctly. So let's see how those calculations can work. We've already done the first several steps in this problem to figuring out the sum. We have broken up the first vector 10 at 30. We broke it up into our x and y components, and sometimes it's helpful to make a little table, especially when you start dealing with more than one vector. So I'm going to label this first vector vector 1. I'm going to label this one over here vector 2. And I'm going to tabulate over here to the side. For vector 1, I have an x and a y component. And for vector 2, I've got an x and a y component. And we've already calculated those out. We figured out for vector 1, the x component was 8.6603. And for vector 2, the y component, or vector 1, the y component was 5. For vector 2, the x component was 5.1423, and the y component is 6.1284. So there we can tabulate the results of finding our components by using magnitude and sine and cosine. And as you gain more experience with these kinds of problems, adding vectors together and such, you'll likely just jump from your calculator right to these. So you'll know, well, for this vector, the x component's adjacent, so it goes with cosine 10 cosine 30, 8.6603, and you'd write that down without going through the whole formal calculation. Now, if you are experienced with this a little bit, or have had some background in it, you may be saying, hey, wait a minute, is x right here in vector 2? You've got it as 5.1423, but it's off to the left. Shouldn't that be a negative? And the short answer is, yeah, it should be a negative, but I prefer to not let signs creep in over here. I like to think of these as legs of a right triangle. The directions are already taken into account with the arrows I've drawn in the picture. And I will take the directions into account when I do my sums, but you'd never label the side of a right triangle with a negative number. So I like to keep everything positive at this stage. I let the directions be held by the directions of the arrows in my picture, rather than trying to tabulate it with positives and negatives. Now, if you don't have a picture, then by default, you'd have to include those signs, because otherwise you're not able to communicate what direction that component is in. So if you didn't have the picture, you'd have to put a negative sign in front of that x component. But just as an intermediate step in doing our calculations, I usually find we don't need to write it in there. We can take it into account in our sum. So let's do the sum here. Now, the reason we are breaking things up into components, the whole reason we're doing this is because we can't directly add vectors in polar, at least not without a lot of extra work. Again, things like law of cosines. You can't add the 10 and the 8 or the 30 and the 40 degrees in a meaningful way to get your resultant directly. We can add in Cartesian by restricting the components to either the x direction or the y direction. We get two vectors we can add up simply. This x component is a vector. it's to the right, and it's got a magnitude of 8.6603. This x component over here is a vector. It's to the left, and it's got a magnitude of 5.1423. If you remember from last time, vector addition, we don't have to care about where exactly these vectors are in the drawing. We can move them around so that they are arranged the way we need them. And if we picked up this vector over here and dragged it down here so its tail was at the head of the x component for vector 1, we could see how we kind of are doing that same number line addition and subtraction that we did on Monday night. Math in Cartesian is easy because it's just addition and subtraction. Math in polar is more challenging. Math in polar is hard to do. So we break the vectors up into Cartesian to make the math easier. We do our addition and subtraction in Cartesian, and then we flip back to polar in the end. So essentially, it's kind of like solving a problem by translation, where we can't really do a translation directly from one language to another, for example. But if we go to an intermediate language, we can translate it back more easily. So it's that kind of process. So let's do our sums. I'm going to introduce a symbol here that you might not be too familiar with, but it comes up very frequently in subjects like this. We use a Greek letter called sigma. It's a capital sigma, and it's drawn out something like this. Looks kind of like an E, but with an M on its side or something like that. It's short for summation. It means to sum or add up. Well, we're going to do two sums. We're going to take a sum of components in the x direction, and we're going to take a sum of components in the y direction. So we're going to sum up our x components and sum up our y components, but we have to take into account direction. So here's where I bring in my signs. I'm going to look at the x component for vector 1. That's 8.6603. So I'll write that down, 8.6603. If I look at the drawing, that's to the right. So it's positive. It goes into the sum positive if it is to the right. Then I'll go down to vector 2. Vector 2 had an x component of 5.1423. But according to my drawing, that 5.1423 is to the left. So it goes into the sum negative. So if a vector is to the left, its x component is negative. If a vector is to the right, its x component's positive. Now we can go to the calculator and key those in. 8.6603 minus 5.1423. That's 3.5180. And here I'm just arbitrarily keeping 5 significant figures. And the question did come up about that on our homework assignment, on our homework 1. Generally, if it's not specified as far as number of sig figs, 5 will keep you safe. Almost every practical problem, it will either be told to you how many sig figs to use, or you'll be able to determine it from the information in the problem. So that's our sum in the x direction. So what does it mean physically? If these are forces, then the amount of pull to the right that we get out of this vector 10 wins over the pull to the left from the 8 vector. Our x component came out positive. So that means that our x component of our resultant is to the right, which is consistent with what we expect our answer to be. We expected our answer from our graphical addition to be to the right. Not quite as much to the right as the first vector is, but still to the right. So 3.5180. Let's do our y components. Well, the y component sum from vector 1, I've got 5, but it is up. So it goes into the sum positive. Vector 2, I've got a y component of 6.1284, also up. Both of these vectors pull up. So both of them have positive y components. So those just add up. 5 plus 6.1284. So we have 11.128. Those are the components of our resultant vector. We have and they're both positive. That means they're both in the first quadrant. We've got 3.5180 to the right and 11.128 up. Any questions on getting the components of the resultant? Everyone feeling okay with where the numbers are coming from? All right, so let's finish the problem by constructing the polar description, the magnitude and direction of our resultant. And unfortunately, things are kind of cluttered already here, so I don't want to draw on top of this. So I'm going to go to another sheet and try and keep most of this right there so we can still see the components. But I'm going to redraw my resultant. So here's my x and my y axes. Here's where we can draw in our resultant components. And it doesn't matter which one you start with, X or Y. What does matter for proper visualization and for getting the right angles set up and all that is that you draw them kind of the same way we drew the components here, with the heads and the tails connected, rather than just drawing them both off of the origin. Think of these components as instructions for getting to the point. So many units to the right and so many units up, or so many units up and so many units to the right. I almost always default to horizontal then vertical. It's arbitrary. It's not what you always have to do or what is necessarily required, but it's just my habit. I go horizontal then vertical. I go X then Y. Maybe it's just alphabetical order. I don't know. But in the X direction, I have 3.5180. So I'm going to draw an arrow, and I'm going to try to be roughly to scale, just to make sure the angles look kind of right. I wouldn't break out a ruler or set a scale or anything like that. It's not that precise. So I have here 3.5180. So that's the length of my X component. Then I'm going to draw the Y component starting where I left off from the X component. And that's going to be roughly 3 times bigger. So I'm going to draw it about there like that. So that's my Y component, and that was 11.128. Now these are vectors. Even though they're components, they are vectors. They're simple vectors, though. They're only along one direction or another. It's either all X or all Y. But since they are vectors, we can add them together, and we can add them together graphically by just drawing a line between the tail of the first vector and the head of the second. Well, that hypotenuse is our resultant vector with some magnitude and some direction. So we've got our components. We use the components of our resultant vector to draw the resultant vector in. Now we can use the Pythagorean theorem and inverse tangent to get our magnitude and our direction. The magnitude, if we're going to use this direction, that angle, then this is the opposite, and this is the adjacent side. So our magnitude is going to be the square root of the opposite side squared plus the adjacent side squared. And if we go to the calculator and key it in, I'm not going to write it all down on the page, and you can double check yourself on your calculator. But 11.128, we'll square that. We'll take 3.5180 and square that. Add those together, take the square root. My magnitude is 11.671. So we get a magnitude of 11.671. That'd be the length of the hypotenuse, the length of our resultant vector. We need the angle. The angle is going to be the inverse tangent of the opposite side over the adjacent side. Well, my opposite side's 11.128. My adjacent side is 3.5180. If I divide those and I take my inverse tangent, I get an angle of 72.456 degrees. So that's the angle. So we have a magnitude here of 11.671 and an angle of 72.456 degrees. That is the result of adding together these two vectors. Now, physically, what that represents is the net effect of applying these two vectors at the same time to the same thing. If these were forces and we had 10 pounds pulling to the upper right at 30 degrees, and we had 8 pounds pulling to the upper left, 40 degrees off of vertical, the result would be a single force of 11.671 pounds to the upper right by 72.456 degrees. That would be the result of those two vectors combined together and applying on the same object. If these were flowing fluids, we'd have the same kinds of directions and angles involved and magnitudes, just with the appropriate units, flow rates instead of pounds. But that's the idea behind adding vectors together analytically. You break the vectors up into components. So that's what we did here. We used sine and cosine and the magnitudes to find out the pieces of those vectors along the x and the y direction. We totaled them up by combining the x components together and combining the y components together. We took our sums. That gave us the components of our resultant. And then we used the components of that resultant to build the magnitude and direction of the resultant vector. That is vector addition. And everyone works exactly the same way. We can write computer programs to do this. So it's the same basic procedure. Break the vectors up into pieces, add the x components together, taking into account directions, add the y components together, taking into account directions, and then use your resultant components to figure out the magnitude and direction of your new vector. Anyone having any questions on that so far? All right, we are just about on our schedule here, so let me go back to the slides. So we'll be doing some more examples here in our practicum session. So the practicum session will start in about 10 minutes. We'll take about a 10-minute break here in a moment. And at 6:30, we'll start our practicum session. I'll lead off the practicum session with another worked through example of adding two vectors together. And then I'll put a couple problems on the display for you to look at and work out on your own. During that process, I'll have the audio on and all that. So if you have any questions that come up, normally in our practicum sessions, I kind of wander around the room and look at your results and see how things are going. But here, obviously, I can't do that online, so I'll just leave the mic open and you can ask questions as they come up, and then I'll work through the solution. So next time, we'll be doing force systems. We'll be getting into into equilibrium problems. So we'll do an introduction to force systems. We'll introduce the idea of free body diagrams, which help us to isolate what forces are acting on a body. We'll look at the concept of equilibrium, and then we'll work on developing the equilibrium equations for what we call concurrent coplanar force systems, which will be the first force system we'll be solving problems on. The background for those equations are what we've done here tonight, being able to add vectors together. Since in an equilibrium problem, all we're doing is combining vectors together. The trick is we have one vector we don't know. So we end up with an equation that lets us solve for the components of our unknown vector. And then we can figure out what that unknown vector is. That's an equilibrium problem. So it's one skill on top of another. So really got to make sure you've got vector addition down. And so we'll do some practice on equilibrium problems. All right. So anyone have any questions there? All right, we'll take a break for about 10 minutes or so, and then we'll be back with another example on adding vectors together and some practicum problems. If you're coming back for that, I'll see you in about 10 minutes. If you're heading out, well, have a good weekend, and I'll see you Monday night.